Okay, now we'll start a question answer series for group theory 1, and this is for semester 2 under Calcutta University course. And first we will give some theoretical explanation and we will continue some previous year problem and solution. And today we will discuss only 5 problems. In that we will continue next 5 to 10 and 10 to 15. That in each day we will continue 5 problems. So first we'll start with the definition of group. So our question is here, question 1, define group. Define group. So here the definition is, let G be a non-empty set. G be a non-empty set and not be a binary operation. Binary operation on G. Then G is said to be group. G is said to be a group with respect to the binary operation not if it satisfies the following condition. So here the first condition is A not B, this belongs to G for all AB belongs to G. That means the closure property holds. Next it holds with respect to not the associative property. So that means A not B not C, that will be A not B not C for all ABC belongs to G. This is called the associative property. And 3, there exists an element E belongs to G such that A naught E equals to E naught A equals to A for all A belongs to G. This is called the existence of identity. And another property related to the existence of inverse. So that means for all A belongs to G, there exists an element B belongs to G such that A naught B equals to B naught A equals to the identity element, and this is called the existence of inverse. Then we said G is a group under the binary operation not. Now when it is, say, if I will give you one example. So here the example is Z plus with respect to addition, the set of integers is a group as it satisfies closure associative existence of inverse and as well as the existence of identity. So that question exactly asked in the year of 97 in Calcutta University examination and 2001. Okay, now you have asked say another question, question 2, define abelian group or commutative group. Commutative group, or when a group is said to be abelian or commutative. So a group G naught is called abelian group, is called abelian group or commutative group or commutative group if A naught B equals to B naught A. That means it holds the commutative law for all AB belongs to G. Then this group is called commutative group. So if we think about the example of commutative group, again Z plus is also an example of an commutative group. So this is an example of a commutative group. Okay, now we will come to the next important question. This is question number 3, and that question basically asked in the year of 1998. See what is the question. Let G equals to set of all matrices 1 n 0 1 such that n belongs to Z. N is an integer. Then show that G is a group. G is a group with respect to matrix multiplication. With respect to matrix multiplication. And next question is this group commutative? Is this group commutative? Justify your answer. Justify your answer. And the marks is here 3 plus 2, 5 marks. So in this question we have two parts. First we will show that it is group, then we will show it is commutative or not. So what is exactly our given set? Our set is G equals to all those matrices of the form 1 0 0 1 where n belongs to Z, and we need to show it will be a group with respect to multiplication. So what is our first part in the question? We shall show that G is a group with respect to matrix multiplication. Matrix multiplication. That means what we will show? We will show it satisfies the closure property with respect to multiplication, associative, identity, and inverse. So first we will come to the property. This is the closure property. Say take any two matrices, say 1 m 0 1, and we take another matrix 1 n 0 1, that is belongs to G. So then obviously m n both are integer, and now if we multiply this to matrix 1 m 0 1 and 1 n 0 1, so that multiplication will be 1 m plus n 0 1, and that is also belongs to G. Why? Because m plus n is also integer, as m is integer, n is integer, and sum up to integer is integer. So what we have seen here, say this is your element A, that element is B. So what we have seen, AB, this belongs to G. So with respect to multiplication, AB belongs to G for all AB belongs to G, because AB is arbitrary. So that means closure property holds, because since A comma B belongs to G is arbitrary. So with respect to matrix multiplication, the closure property holds. Now we come to the property associative. We know the matrix multiplication is associative, and G is subset of M to R. So by hereditary property, we can say easily it holds the associative property. So next is for associative property. So by standard property of matrix multiplication or by hereditary property of matrix multiplication, so we must say it is associative with respect to matrix multiplication. So associativity holds with respect to matrix multiplication. Matrix multiplication. Why? Because since that we know the properties matrix multiplication, this is associative. Now we come to the next important condition. We need to satisfy the existence of identity. So existence of identity, say here we will take the matrix I2. This is basically 1, 0 and 0, 1. And that obviously belongs to G. Why? Since 0 is an integer. So that means therefore for all A, this is equals to 1 n 0, 1 belongs to G. There exists the identity map belongs to G such that AI2 equals to I2A equals to A. So that means the existence of identity that is also holds. Now for existence of inverse, what we will do, say we have take let 1 n 0, 1, that element say A belongs to G. So we need to show the another element B, so that AB equals to BA, that will be identity. So then what will be A inverse? So A inverse will be 1 n 0, 1, that inverse, and you know that will be 1 by AD minus BC, so 1 1 minus 0 n, and the principal diagonal interchange, the off diagonal you will just multiply by minus sign. It will be minus 1 and 0. So that means because we know that we recall some fact, if A equals to ABCD and date of A is non-zero, so then A inverse exists, and A inverse will be 1 by AD minus BC, principal diagonal interchange, and off diagonal just you multiply by minus sign. So that means it will be 1 minus n 0, 1, and that is also belongs to G. Why? Since n belongs to Z, must imply minus n is also an integer. And we see that here A inverse equals to A inverse A, that is basically identity. So for each element, therefore, since A is arbitrary, therefore for all A belongs to G, there exists A inverse that is also belongs to G, such that A inverse equals to A inverse A equals to identity. So existence of inverse is also holds. So that means we can conclude therefore G with respect to multiplication, that means G is a group with respect to matrix multiplication. Okay. Now we come to the next part, that means second part of the question paper. Second part, what is asked here? It has been asked it is commutative or not. So we'll check. Okay, it is commutative or not. So we'll take any two element. Let A equals to 1 n 0, 1 and B equals to say 1 m 0, 1. Both are belongs to G. So that means then n and m both are basically integer. So now what will be AB? So AB will be 1 n 0, 1, 1 m 0, 1, and that is basically 1 n plus m and 0, 1. And also if we calculate BA, so that will be 1 m 0, 1 multiple 1 n 0, 1. Again it will be 1 m plus n 0, 1. Now from that we can conclude AB equals to BA. Why? Since integer, z plus is commutative. So since n plus m equals to m plus n for all mn belongs to z, as z with respect to addition is commutative group. Commutative group. So therefore this holds for AB. Since AB is arbitrary, so we can write AB equals to BA for all A comma B belongs to G. So commutativity property holds. Therefore G with G is commutative. G is commutative group with respect to matrix multiplication. With respect to matrix multiplication, their answer is yes. It is a commutative group. It is a commutative group with respect to matrix multiplication. Matrix multiplication, and this is just our justification. So we have done the justification here. Now we come to next important property. Next important question. The question is true or false. Question number 4. Question 4, and this question is asked the year of 2003. The question is true or false. True or false. Justify. Justify. So you have given M2 equals to set of all matrices of the form 2 to the power m 0, 0, 3 to the power n, where m and n are basically non-zero integers are non-zero integers. Non-zero integers. Then what we have to check, then it is said M2 forms a group with respect to matrix multiplication. With respect to matrix multiplication. Multiplication. You need to show that this is true or false. So we know if a set, an non-empty set forms a group with respect to some binary operations, it satisfies the closure property associated with existence of identity and existence of inverse. So if one of the property is basically does not hold, then we can conclude this is not a group. So what is our M2 here? Our M2 equals to all those matrices of the form 2 to the power m 0, 0, 3 to the power n, where mn belongs to z minus 0, because it is said it is a non-zero integers. So now we will say if we think about the identity element, so yeah, the identity is basically does not exist. Why? So I am writing here the statement is false. Statement is false. So if I say false, we need some justification. So what is our justification? Here M2 is this. Now the statement is false because the statement is false because the identity matrix cannot be, that is I2 equals to 1 0 0 1. This is basically identity of the element. So identity of the set. So cannot be written as 2 to the power m 0 0 3 to the power n for non-zero mn. So we can't write it, the identity, because if we find 1, so 1 will be 2 to the power 0, so 0 is not in the set. Okay, z minus 0. So you can write it in that form. So obviously because identity element is basically does not exist, so it is not a group. So therefore M2 is not a group with respect to matrix multiplication. Matrix multiplication. Okay. Now again there is another question. The question is question number 5. Question number 5. This question is given in the year of 2008. What is the question? Let M2 equals to matrix of the form XI-XI such that x comma y both are real number and x plus y is non-zero. The question is, does M2 forms a group with respect to matrix multiplication, forms a group with respect to matrix multiplication. So justify. What is R? R is basically the set of all real numbers. Set of all real numbers. Now we come to the solution. So how to solve? How to show if it is a group? So closure associative existence of identity inverse. So all the property holds. So the similar argument as previous problem. Here state that no M2 this is equals to XI-XI such that x comma y belongs to R and x plus y is non-zero. M2 is not a group. Not a group with respect to matrix multiplication. With respect to matrix multiplication. So here we need justification. Here we need justification. So what is the justification? Because it does not contain the identity matrix. The identity matrix I2 equals to 1, 0, 0, 1. Why it does not contain? Because it is which is not of the form xy and xy. Okay. And if you check here, so identity matrix will be the identity element, but that element does not belongs to M2. Okay. Because if you take x equals to 1, y equals to 0, so it will not form an identity matrix. So where x comma y are real number and x plus y number. So it is not in the form. So that's why it does not contain the identity matrix. So therefore M2 does not contain the identity element. So M2 is not a group with respect to matrix multiplication. Thank you so much. In the next class again we'll do 5 important problem. Obviously previous year problem which is exactly set up by the Calcutta University examination in different year.